In this section, we will look at ionic bonds, metallic bonds, and covalent bonds. They are ways that the elements combine, and they're all slightly different. So we'll look at each one. So we're starting with ionic bonds. Remember, your ionic bonds have a metal and a nonmetal. So the metal will donate one or more electrons. The nonmetal will accept one or more electrons. So over to the right here, you have an ionic bond. You have sodium combining with chlorine. Sodium normally has one valence electron. It will give up that one valence electron, and the chlorine will accept that one valence electron. And when sodium gives up that one, then the next shell to have any electrons is one further in, and it has 8 electrons, which is the way your noble gases are. And your chlorine, once it accepts that electron, also has 8 electrons in its outer shell, which is how your noble gases are. So you'll notice they combine in such a way that they both have an electron configuration that looks like a noble gas. Of course, when it does that, it throws off the ratio of plus to minus charges in each of those atoms. The sodium becomes positively charged because it has one more proton than electron, and your chlorine becomes negatively charged because it has one more electron than protons. And you'll end up with this 3D lattice of these charges coming together because plus and minus charges attract, just like the north and south pole of a magnet does. That's kind of that same phenomenon on a larger scale when you see that attraction going on between a north and south pole. So here we have a lattice of sodium chloride off to the side here, and you've got 1 plus between the 4 minuses around it. No, let's see, 6 minuses around it. And if you look at a minus, you'll see there are 6 pluses around it. And so they kind of stabilize each other's charges by forming a lattice like that that's 3D. So in ionic compounds, you have these metals and nonmetals combining so that they get a noble gas configuration of electrons. And sometimes those numbers match up beautifully, and you get the same number donated as accepted. And sometimes they don't. Sometimes you get a different number donated than accepted. And when that happens, then they combine in ratios that are other than 1 to 1. So for example, calcium is in group 2, so it's going to want to donate 2 electrons to empty out its outer valence. Chlorine is in group 7, it only wants 1 because 1 will get it to 8. So when they combine, 1 calcium will combine with 2 chlorines, and the calcium donates its 2 electrons. Each chlorine accepts 1, but because there's 2 of them, there's a place for those electrons to go, and you get CaCl2 as calcium chloride. If you have barium and you have oxygen, your barium is in group 2, it's going to want to donate 2. Oxygen is in group 16, it's going to want to take 2. Notice that lines up perfectly, so you only need 1 to 1. 1 donates 2, 1 takes 2, they're happy. So you get barium oxide as just BaO. And there's no 1s written there because if there's nothing written, it's assumed to be 1. If you have potassium, that's in group 1, it's going to want to donate 1. And sulfur, which is in group 16, it's going to want to take 2. Well, 1 potassium isn't going to be able to provide what the sulfur needs, so it'll take 2 potassiums, each donating 1, to provide the 2 electrons that sulfur wants to get to its 8 valence. And so you get potassium sulfide as K2S. Iron actually comes with a couple of charges, but there is one way that it comes with 3. And bromine comes as 1 minus. Your transition metals sometimes have multiple possibilities. Bromine is in group 17, so it's going to only want 1. And so it will take 3 bromines to combine with 1 iron. And you get iron 3 bromide with the iron taking 3 bromines in order to actually get rid of all of its electrons. Chromium can also have a +3 charge. Oxygen would have a 2- because it's in 16. And when those two combine, you're going to have to combine so that you've got 6 electrons donated and 6 electrons accepted, because 3 and 2 don't really square off directly. And so you'd end up with Cr2O3 in order to make that balance. Same sort of thing happens when you combine aluminum and oxygen, because aluminum is 3+, oxygen is 2-, and so the only way to make those balance, the lowest common multiple of 3 and 2 is 6. So we'd have Al2O3 to get 6 electrons donated, 6 electrons accepted. Then we have metallic bonds. Now we're not going to deal a whole lot with metallic bonds here, but they're quite fascinating because the metallic bonds often make up the metals that you have in your bridges, the metals that you have in your wires. They're often not just a pure metal. So in order to combine metals, you're going to need a metallic bond. Those metals combine together, and when they do, what keeps them together is they share electrons. Those electrons start flowing freely, all the valence ones, between all the nuclei that are in the substance. So this explains a lot of the properties for your metals. Because those electrons are flowing freely, if we apply electricity, which is electrons, to one side of something that has metallic bonding, then electricity will come out the other side. So they work well as conductors. If you heat up something with a metallic bond, then it will allow that to vibrate, and so they end up being able to heat up really fast. So you can do heat conductivity. You may have noticed if you sit in front of a fire with a necklace on, that necklace is rarely a pure element of any sort, but it has metallic bonding going on in it. And as you're just barely beginning to warm up, the necklace or maybe a metal zipper on your coat will heat up to the point that it's like burning you. It's really hot. And the reason is because the metallic bonds absorb heat really well and really quickly. They also let off heat really quickly. So when you go out skiing, you know that necklace gets really cold before you're really cold. And then there's also, because those atoms are not singly bonded to each other in any way, there's a malleable thing that can take place with your metals. You can bend them, you can hit them and cause a dent in it. So they have excellent malleability when they're just a metal. If they want to throw that off, they'll put in some impurities like carbon and stuff to make things stronger so that they don't bend quite so well. Then the third type is covalent bonds. This is when you get two nonmetals together. Now nonmetals, they each want to add more electrons to what they're doing. But because they all want to add, the only way they can do that is if they start sharing. So they'll get together and they form what's called a covalent bond. They'll share 2 electrons, or a few elements can share more than 2. Those elements are cons. They can share 4 between the 2 nuclei, carbon, oxygen, nitrogen, and sulfur. And 2 of them can actually share 6. And that is just carbon and nitrogen. They're the only 2 elements on the periodic table that can share 6 electrons. And when they share 6, they get a triple bond, and so you'd put 3 lines between them. When you have 2 shared, you'd put 2 lines between those elements to show that there's actually 4 electrons there. And whenever you see a line between elements, that represents 2 electrons that are shared. So here to the left, we have 2 oxygen atoms, and you'll notice that they're sharing 4 dots, 4 electrons. So O2, the bond there is actually called a double bond, and it has 2 pairs of 2 that are shared. And some examples over to the right here, we have a carbon. Carbon needs to form 4 bonds. So if you have carbons that each have 2 hydrogens, they still need to form 2 more bonds. They'll form those between each other if need be, and you'll end up with a double bond between carbons. If those carbons only had 1 hydrogen each, well then they'd still need 3 more bonds, and they can actually form those 3 bonds between those 2 carbons by sharing 6 electrons. So carbon can be really flexible there, and that'll come into play in chapter 19, that we have whole groups of molecules based off of carbon that are in life because of all the things it can do bonding wise. So here's an example of covalent bonding. We have hydrogen. Hydrogen wants to be like helium. Remember, helium's the one exception there. Instead of having 8 valence electrons, it has 2. So hydrogen would like 2, and oxygen would like 8. And so you have 2 hydrogens, each donating 1 electron, and they pair up with 1 electron on the oxygen, and you get 2 valence electrons for the hydrogen, like helium, and you get 8 valence electrons for the oxygen, like its neighboring noble gas. All the remaining ones other than helium are like that, and you end up with water.